Hi everyone, I'm Matan, a research scientist at NVIDIA, and I'll present our work on approximately piecewise E3 equivariant point networks. In this work, we are interested in improving the generalization capacity of networks tackling 3D tasks, particularly tasks that involve complex scenes with multiple objects. One example of a task that we would like to tackle is scene segmentation of real-world room scans. Since in real-world settings, labeled data availability is limited, we aim to find architectures that efficiently exploit data. Our approach to overcome limited data availability would be to suggest an equivariant network design that can respect more complex scene symmetries than existing designs. What are some symmetries that scenes exhibit? To better understand this, let's consider a segmentation task of a 2D toy example illustrated here with the input on the left and the expected segmentation prediction result indicated by the different colors in the middle. One prominent symmetry of this task is the Euclidean motions, where when it is applied to an input scene, segmentation predictions are invariant. However, upon closer examination of the possible symmetries the segmentation task induces, we notice that in fact each object can undergo a different motion, that is, a piecewise Euclidean motion, for which we expect the segmentation prediction to be invariant as well. Unfortunately, modeling the piecewise Euclidean motion symmetry is challenging, since it requires knowing the underlying input partition that defines the piecewise Euclidean motion. But of course, the partition information is generally unknown. It is intertwined with the segmentation task the model is faced with. Therefore, we conclude that the piecewise Euclidean motion symmetry can only be approximated. Thus, we argue that one should somehow generalize the usual equivariance definition with some notion of approximation. We will refer to the error that arises from satisfying the equivariance constraint by the equivariance approximation error. Which leads us to the main question our suggested design needs to address. How can we formulate a piecewise E3 equivariant design that enables controlling the resulting unavoidable equivariance approximation error? To address this, our suggested solution utilizes the following very simple fact. Consider two symmetry groups, G and G prime, with G prime being a subgroup of G. Then any G equivariant function is also a G prime equivariant function. To understand how this fact is relevant for piecewise equivariant functions, let's look at an example of a piecewise equivariant prediction such as point votes, illustrated here with the arrows. In a case where the piecewise function is defined with respect to a partition that is a good subpartition of the ground truth partition, we can expect a zero equivariance approximation error. Whereas if the function is defined with respect to a bad subpartition, that is, it includes at least one part consisting of points mixed from two different parts in the ground truth partition, then an equivariance approximation error is possible. But why is it useful? It gives us a probabilistic model for a partition prediction model with controllable bounds on the equivariance approximation error. However, this might seem like a too simplified solution, as this might potentially over-reduce model expressivity, leading us to suggest a compositional network design where the complexity of the underlying partition is gradually decreased. In our design, each piecewise equivariant layer also parameterizes the prediction of a coarser partition. All of these ideas are formalized in the paper with the definition characterizing bounded piecewise equivariant functions and a suitable construction supporting it. Please look at the paper for more details. In our first experiment, we considered the task of segmenting real-world room scans, where each room was captured with different timestamps, with room furniture moving between timestamps. We test our method in the one-shot settings and compare versus baseline methods that capitalize large synthetic datasets for training. Note our baseline struggle with consistency across all possible deformations, whereas our method is stable. We also validated our method on human body scan segmentation, showing the superiority of our method over several equivariant and non-equivariant popular baselines. We demonstrated it both quantitatively and qualitatively. Thank you very much for listening.